All right, in this lesson, it'll just be a continuation of equations of lines, except now we're going to be focusing mainly on three space. All right, and what the equations look like. You'll notice that they're very similar to the two space equations, just with one more added component when you're looking at the component form. So your vector equations, that looks pretty consistent from the two-dimensional version. And the meanings are exactly the same. So you have in component form the three components now because we're referring to three space, x, y, and z axes. You still have a position vector to a specific point in three space. Still have a parameter t. And now we have a direction vector in three space. All right. So the direction of the line is a, b, and c. Parametric equations, again, in two dimensions, you would not have this third component. But since we're talking about three dimensions, you will have three. So not really a big change there. Still looking at the same sort of setup and the way it works. Now, symmetric equations, written a little bit differently than what you saw previously, but works exactly the same way. And these highlighted parts we'll talk about in a moment to see what they are. But again, it would be the same as solving for t in the parametric equations, and then setting this equation here. Now, you're really used to having an equation with two equal signs, but that is something that's valid in math. We have three different expressions equivalent to one another. A little unusual, but let's take a look at the different ideas in terms of what those represent. One thing to keep in mind, though, unlike two dimensions, there is no scalar equation of a line in three-dimensional space. So that is very important to note. So if you're given a scalar equation of a line, you automatically know you're in two dimensions. Okay. So just to maybe just quickly do this, so the x0, y0, and z0, those are the values from the point, okay? So from the position vector to a specific point on the line. The a, b, and c, whoops, sorry, are the direction numbers from the direction vector, okay? So that's why they're highlighted there, just to kind of make that sort of connection between the three different values there. Okay, so here's a sample problem. We'll go through a couple and then a little visual, and hopefully it'll work out the way I want it to. So if you're given a line defined by a symmetric equation, now you haven't seen it yet, but so your equation's going to look like this. You got to get used to the different names. You want to write it as a vector equation. So you want to write this kind of equation in this format. So if you look at the variables, it's not going to be that challenging because you need to put the a, b, and c in the correct spot, the x0, y0, and z0 in the correct spot. But you are asked to find a direction vector perpendicular to the line. That'll be a little bit more challenging, but not much. Okay, so again, so take a look at, this is the vector equation that you're asked to find in component form. So position vector to a point on the line. Now, where is that coming from? Not as obvious as you might think, all right? So it seems like the 3 is coming from here, and what's going on there? So oftentimes when you're given these type of symmetric equations, it can be challenging slightly to figure out what goes where. But let's take a look. So we have this part right here. So let's just focus on that for a moment. So if we rewrite the symmetric equation in the format that it's required. So your x, y, and z variables must have +1 coefficients. Take a look what you have here, +1, +1, +1. So that means the -1 must go to the denominator. Why? Well, because if you're going to have a subtract something, to keep it as an x, it has to be a 0. Okay, so it's a little bit challenging to come up with this kind of quantification in terms of simplifying there. This is straightforward. This is already done for you. So it's in the proper format. So you have y, take away something, divided by a quantity. And again, the y coefficient is positive. Here, the z coefficient is positive, so you must be subtracting nothing. And then the value is 4. From this format now, you can then read what you need to read. So in terms of the green values here, the -1, 2, and 4, that represents, as you can see, the a, b, and c values. So that is why those values appear there. Those are the direction numbers and in the proper order. So the x component, the y component, and the z component written in the proper order, x, y, and z. Okay, And then these values, the 0, 3, and 0, are the position vector component values. Now keep in mind if these little symbols in here were pluses, for example, so this was a +3 and not a -3, because of the generic name setup of the formula, then this would be a minus. Okay, so keep that in mind. A little bit like maybe a grade 10, you know, when you're finding the H and K or the H value and looking at a vertex form, kind of a little bit like that. Similar anyways. So there's task 1, so there's your vector equation. Okay. Task 2 was to find a direction vector perpendicular to the line. Well, by now you should realize that perpendicular implies either a dot product, maybe even a cross product, but in this particular instance, dot product is the way to go. So there's your direction vector. Okay, so the direction vector of the line is 1, -1, 2, 4. The direction vector and the vector you're trying to find in terms of the perpendicular one, or the normal, like we discussed earlier. So you can name it anything you want. You can call it n for normal, or you can call it v, just pick generic variables. So you're trying to find x, y, and z. So the dot product between these two, just multiplying and then adding together to get this expression, that dot product has to be equal to 0. So much like we've done before, where we've just picked generic values to find other values, it's just solving an equation. So you get to pick two numbers in this particular case. So I've decided to choose the number 1 and 2 for x and y. Could have been two numbers for y and z. Could have been a number for x and z, doesn't really matter. Then solve for z. It's okay that it's a fraction, that's not a big deal. So then the vector that you're looking for that's perpendicular to the line would have an x value of 1, a y value of 2, and that would be your z value. And of course, there's going to be an infinite number of possible vectors that are perpendicular to the given vector that you have. Okay. All right, so sample problem 2. So here you're given a vector component form, and you're told it's perpendicular to the line given by this here. So it is 3 dimensions. You can see the 3 different components. And what do we need to do? So we already can identify the direction of the line. That's helpful. Okay. And so we're trying to determine if this vector, is perpendicular to the line. Okay. So the quickest way to do that is to take a look at this vector and the direction vector. So if we have a line and we're trying to prove that this vector is either perpendicular or not. So that could be 90 degrees, it could be 80 degrees. Best way to prove that, take the dot product and check to see if it's 0. That's important. So it's a check. So that's a pretty simple process. Find the dot product. In this case, it's false. So if that's false, then your vector v that has been given in this example is not perpendicular to the line. Okay. All right. So as far as this third sample problem here, so we're asked to find a vector, parametric, and symmetric equations for the line that passes through a particular point given a direction vector. So we're given some limited information again, but think of this as like a grade 9 situation. You're given a point, you're given a slope, you have to put the equation together. So you need to know the different formats. So your vector equation has the form like we talked about earlier, right here in component form. So you need a position vector to a specific point and then the direction vector. So we have a specific point. So that's pretty straightforward. So there's the generic component form. There's the specific position vector to the specific point. Direction vector is already given to us. All we need to do is put in a parameter. Why did I choose K? I don't know. Doesn't really matter, to be honest with you. You can use the letter T if you wish. Any parameter will do here. Generally speaking, the letters K and T will work. Stay away from things like X, Y, A, and B, though, because they sometimes can be misleading when you're dealing with other types of forms. So from here, it's easy to get the symmetric equations. Whoops, symmetric equations there. So again, your parametric equations would probably be first. So you take the X values, write that out as an equation. And then you take your Y values, write that out as an equation. Now notice it is important to write L for line, then the colon, then these big giant brace here, open brace, write the equations for each one. And notice the way I've written it here, it doesn't have to be the variable first, so just go in order. So 2, and then here we have a k in the -1, so it's -1k, and then 4, and then the k in the -3, and then lastly the 6 and the 2 and the k. All right, and then here, once again, we can solve for k in each one of them. So subtract 2 from both sides here, and then divide by -1 to get the x portion. Subtract 4, divide by -3 to get the y portion. And then subtract 6, divide by 2 to get the z portion. Now, you might be wondering, why is that not good enough? Well, I think it is, personally. However, you may find that solutions online and textbooks may write the equations this way, which can be very confusing as to why they would do that. To be honest with you, I don't have a specific answer as to what's proper and what's not. Both, I think, are fine. Whatever format you think is comfortable for you. Just keep in mind, if you're checking answers in the back of a book or online, that the format may differ from what you have, just that as long as it's algebraically equivalent, you'll be okay. All right, so did we successfully do everything? We did. We found the parametric, the vector, and the symmetric equations for each one of those. Okay. All right, and one of the last problems we're going to take a look at. So to describe in words, now this can be a bit tricky, and it's something that needs a little bit of practice, but if you can't get a handle of it, I wouldn't worry about it too much, because it can be kind of confusing with different languages or different websites and textbooks too. So you're asked to describe in words the line described by the following parametric equations. Now, how you would describe it is not necessarily how a physics person or you might see in the textbook. So I'm trying to give you some hints as to what's going on here. So I'm going to explain what the answer would look like in terms of comparing to what you see in the back of the book, and then kind of maybe hopefully give you a visual, as long as it works out for me, to show you how this works. So staring at these three equations, these are obviously parametric equations, doesn't really tell you a whole lot, but if you're trying to find what point it passes through, now that you can identify by looking at the parametric equations and those constant values. Okay. Other than that, so you can get that point. So that's pretty much the easy part. Okay, so there's the x, the y, and the z components for the point that it's passing through. So that's simple enough. What becomes more challenging, though, is this part here. What does the direction vector tell us? So the direction vector here is 0 because there's no parameter, so it has to be plus 0t. Here it's a 1t and a 1t, so there's your direction vector. So what does that tell us? Well, because the x component of the direction vector is 0, that goes back to a concept that we looked at way back when we first looked at vectors in terms of discussing something called a plane. It was a very minor discussion, but it did happen earlier on in the discussion of vectors. So this is on the YZ plane. Now, in terms of the language here, because the x component is 0 and the y and the x are any numbers, it doesn't have to be 1, it can be any numbers you want, then that means it has to be on the YZ plane. So I'll give you a little visual. So the line is on the plane that is parallel to the YZ plane. Okay, so that's the proper language. So this is a good one, but then to get even more in depth in terms of the language, let's take a look at how this would work visually. Okay, so we know the line passes through the point -5, 2, and 2. And the direction vector is 0, 1, 1. So that's on the YZ plane. So that's on the YZ plane. But why are we using the parallel to? So let's take a look and see if we can figure this out. So here's the x, y, z axes. And you may have the x and the y slightly different, but that's okay. So the YZ plane, let's see if I can just draw this out. Hopefully it'll work for me. If I draw this out, the YZ plane kind of looks like this here. So hopefully this will work. There, worked out pretty good. Okay, so I'm going to just slightly change the colors here just so you can get a decent visual anyway. And we'll lighten this up. So there's a plane. So it should go on forever, but that is the YZ plane. Now the vector that we're looking at in terms of the direction that the line follows is 0, 1, 1. So let's take a look at that. 0, 1, 1. 0, 1, 1 implies 0 along the x, 1 along the y, and 1 along the z. So this is using isometric paper. So there you can see the direction of the line. Now, the only issue here is that the point that the line passes through is given to you right here. So if that's the point, then the point is actually, well, let's take a look. -5 is 1, 2, 3, 4, 5, 1, 2, 1, 2. So the point it has to pass through is back here. So what essentially has to happen is this plane has to move all the way back there. So there's the point on the line. And then your direction vector follows the same pathway. So it just goes there. And that's the direction of the line. But if you're actually drawing the line itself, let's see if we can get a good handle on this. Let's make it bright red. Okay, so the direction of the line would have to be passing through that kind of idea. Okay, so that would be the line. I've made it kind of small, but let's maybe make it a tiny bit thicker so you can actually see it as a line. So it's following this direction, but it's on this plane. Okay, so it is kind of sneaky. So you have a direction as to what it's following, and that tells you it's on a certain plane. So it's parallel. Notice that this blue is parallel to the YZ plane because that's what I originally drew it, but then I shifted that plane 5 units in the negative x direction, and that gives you a better description in terms of what's going on. So hopefully that gives you a decent visual in terms of the language that you will see for these types of questions. Okay? And that concludes the examination of lines in 3-space.